Hello everyone, welcome to this presentation. I am Nahian Ibn Hassan and the title of our project is Synthetic Virtual Head Model Generation using Generative Adversarial Network or GAN. Synthetic data is used for various purposes such as data augmentation. When you have few amount of data, you can generate new synthetic data. There are different ways you can generate synthetic data, but here we are going to use the generative networks. Most of the time, population-based studies do not have enough subjects or MRI data to conclude on statistical inference. Statistical inference require a large number of experiments. In this project, we are going to generate this large amount of data or the synthetic data using real MRI head models and then compare the quality of the generated images. So this is the overall project workflow. In the first stage, we are going to generate virtual head models using real MRI data using the software SimNIBS or FreeSurfer. SimNIBS is a cortical-based surface extraction tool and it uses the FreeSurfer or FSL in the background. Next, we are going to voxelize the FEM mesh and extract a single slice from each of the subjects. Using those slices, we are going to train a generative adversarial network. The final two steps are the post-processing, which includes some of the image processing techniques and the evaluation of the generated images. For evaluation, we are going to use the FID score or the tissue area extraction. We are going to into the details within a couple of minutes. So the database that we are going to use is from the Human Connectome project. You can refer to this database from this link that I have shown here. The data are structural MRI scans and they are from either 3 Tesla or 7 Tesla MRI coils. The type of MRI scans are T1 weighted and T2 weighted. There are 812 subjects in our database and those subjects are within the range of 22 and 35. And we have equal number of males and female subjects. So step 1 is generating virtual head models from the real MRI images. So you have the MRI scans and you pass the MRI scans to the SimNIBS or FreeSurfer pipeline and the output is a co-registered finite element mesh. Here I am listing some of the major steps that are used to segment and mesh the whole brain, but there are other sub-processes. It's a huge workflow implementing different image processing steps. The toolbox co-registered the head models in a common frame facilitating group level analysis, and the head models have a high fidelity. Then it uses bias field correction, it extracts the human brain from the skull, it divides the whole brain into left hemisphere and right hemisphere, it extracts different tissues like the white matter, gray matter and other tissues. It solves different imperfections and it finally generates a finite element mesh. So I'm not going into the details of any of these steps, but if you're interested, you can refer to this reference here. So step 2 is generating voxelized heads from the finite element mesh. The voxelization grid is an important factor here. As you can see, for lower grid sizes, the tissue boundaries are not so well defined. The tissue boundaries become prominent with grid sizes beyond 128. So higher the grid size, the better the tissue boundary resolution. But for higher grid sizes, the computational effect comes into play. As you can see, the best quality of voxelized head model is achieved by 512 grid size, but it becomes humongous in terms of data size. So training a 3D neural net with large amount of data like this becomes impossible, and that's why we are going to use the 256 grid size data. So step 3 is extracting a mid-cortical slice. Since the project is 2D synthetic data generation, we will focus on single slice. For that, we have chosen the mid-coronal slice for each of the subject. You can also see the effect of voxelized grid size on 2D slices as well. Okay, so we have generated the data. Now we are going to train the generative network with these voxelized data. But before that, first I will give you a brief introduction about the GAN. Generative networks are comprised of both supervised and unsupervised network. It has two different networks. One is the generator and the other one is the discriminator. The purpose of the generator is to produce fake data or synthetic data, and the discriminator tries to find out whether the generated images look like real images or not. So it's a simultaneous process. Both networks are trained simultaneously. Neither of the networks can well trained. Because if the generator is trained too well, whatever image is generated, the discriminator will consider it as a real image. And hence, in subsequent iterations, the generator will be penalized less. As a result, the generator will stop to improve. On the other hand, if the discriminator becomes too good, the generator will be penalized largely. As a result, it will be harder for the generator to reach an equilibrium and start to generate good images. So it's an equilibrium game. Both networks will be trained together, but no one will win. We have to reach at an equilibrium, and that's why training a GAN is challenging. Over the years, researchers have improved GAN. You can see the improvements in generating fake images over the years. Recently, people have become more interested in 3D GAN. One of the research groups from MIT are doing research on 3D object reconstruction. So it adds an extra dimension of complexity in generating fake data. Now think about our project. These 3D objects are geometrical and well-shaped. However, if the shape becomes too complex and uncertain, like the human brain, it becomes even harder, and therefore the focusing on a single slice, like the 2D data, is our main purpose. But the ultimate goal is to generate 3D synthetic head models. We are focusing on style GANs. Style GANs have become successful in recent years in generating 2D facial images. I'm not going into the details of style GAN architecture. However, if you feel interested about style GAN, you can refer to this reference here. Let's see our project progression. First, we tried to generate 3D synthetic data, but due to huge computational and memory burden, we had to reduce the network parameters by over 50% and train with short batch sizes, like 1 to 2 images. As you all know, training a neural net with short batch size and small network is not a good idea, and that's what happened here. The generated images are just some random distributions. So in our next attempt, we tried to focus on a single slice and single tissue, for example, the white matter. So this time the network is well trained and it generates synthetic white matter tissues which almost resembles the original white matter tissues here. So seeing this result, we decided to train our network with all the different tissues that we have. So here is our next attempt. We have now considered all 5 different tissues: the gray matter, white matter, CSF, skull, and scalp. As you can see, the style GAN produces some realistic head tissues, but you also can notice that there are some noises and tissue boundary imperfections in the synthetic images. So we need to post-process them and construct a uniform head slice. Therefore, our next step is post-processing. The first step of the post-processing is image quantization. Because GAN generates images with distinct tissue numbers and with multimodal Gaussian distribution, we need to quantize those images. In our case, we have 5 modalities corresponding to 5 different tissues. Hence, we need to label each pixel corresponding to each tissue with some unique labels. As you can see, the quantization tissues are much more prominent than the immediate generated GAN images. However, the tissue boundaries are not well defined yet. That's why we go for further processing. 2 image processing techniques that we frequently use are image erosion and image dilation. A combination of both of these techniques reduces the island-like small noises here and constructs a continuous tissue boundary, as you can see here. Next, we extract the tissue outer boundary to find out the exact boundary between different tissues. So here is a summary of our post-processing steps. We applied the image quantization, image erosion, image dilation, and contour extraction method for all different tissues separately. And finally, this is our final processed head slice. Alright, our final step is to find out the quality of the generated images. First, we decided to evaluate the quality of synthetic images by comparing the tissue area distribution between real and synthetic data. But it turns out that the generative network produces almost uniform distribution of tissue areas at different training steps. In the process, the network first decides how many pixels should be assigned to each tissue, and after that it starts to change the spatial distribution of the tissues. And that's why we have decided that tissue area is not a good candidate for evaluating the performance of generative networks. So anyway, we still show here the comparison between the synthetic and ground truth data distribution different tissues. The distributions are almost equal and well within the 20 to 80 percentile of the actual distribution. Similar cases here as well. Anyway, our next metric is the Frechet inception distance score. It uses the inception network and it extracts the probability distribution of the fully connected layer of the inception module for both real and synthetic images. We tried to see what is the effect of voxelization grid result. As you can see, for lower voxelized images, the FID score doesn't improve. However, for higher grid sizes, the FID score starts to decrease with respect to iterations, and that is our purpose. The lower the FID score, the better the quality of the image. So the summary of our project is that we have successfully completed all of the required steps of project outline. The voxelization grid is an important factor in image quality and training the network. The style GAN generates synthetic images very well, but it requires substantial number of iterations before generating any meaningful image. The area of the tissues does not predict the quality of the synthetic images at any training iteration. And the FID score also improves with respect to training iteration, but it's meaningful for higher voxelization grid size. So we have a drawback in this process. The sliced images that we have used for training the images, they does not correspond to the same cortical plane across subject, because across subjects we have the difference and uncertainty in the structure of the brains. So in future we are going to use the MNI coordinate system to extract the same cortical plane across subjects, and we are going to extend this concept to 3D style GAN, which will require us to explore the multi-GPU processing techniques. So here are some of the references that you can reference to, and thank you so much for staying tuned.